fascinating core of complex stuff. Today, we're really diving deep into one of the most, well, mind-bending concepts in physics. You've probably heard it, Albert Einstein's famous phrase, spooky action at a distance. And this isn't sci-fi. It's the reality of quantum entanglement, particles linked in ways that just defy common sense.
Excellent.
So our mission here is to unpack some brilliant questions you've brought up. You've got these really intuitive ideas, what you called wave function inversion, and also this elimination of possibilities in quantum systems. We want to take those ideas and see how they map onto the, let's say, precise language of quantum theory. We're drawing on a formal analysis about state correlation and collapse. Get ready, because, yeah, this is where reality gets pretty weird and fascinating. Okay, so to really get this spooky action, we probably need a quick refresher. The basics. What exactly is a quantum state? How do physicists even talk about this stuff?
Right. So, at its core, a quantum state is described mathematically. We use something called the wave function, often written as psi, the Greek letter. Now, it's not a wave like in the ocean, nothing physical like that. It's a complex valued function. It lives in this abstract space physicists call Hilbert space.
Hilbert space. Okay. So like a mathematical arena.
Kinda, yeah. Think of it as the space containing all possible states for the system. And crucially, this wave function holds all the information you can possibly have about that system.
All the possible information. So it's not like a snapshot saying it is here.
Yeah.
More like probabilities.
Exactly. It gives you probability amplitudes. You can't measure an amplitude directly. The connection to what we do see, what we measure, comes from the Born rule. Max Born, 1926. It says the probability of getting a specific outcome is the absolute square of its amplitude.
Absolute square. Got it.
Yeah. And this is fundamentally different from classical physics, you know? There, you assume you can know everything precisely. Here, probability is just built in. It's actually funny, Born himself apparently misinterpreted his own rule at first. Shows how counterintuitive it was.
Huh. Okay. So if the wave function maps out possibilities, what about superposition? This is where it gets really wild, right? A particle being multiple things at once.
That's superposition, yes. The principle is simple. If a system could be in state A or it could be in state B, then it can also be in any combination of A and B. And it's not just that we don't know which one it is. The system is, in a very real sense, in all those states simultaneously until you measure it.
The double slit experiment is the classic example, isn't it?
It is. Single electrons, one by one, somehow create an interference pattern, like they went through both slits. But if you try to check which slit, put a detector there, boom, the interference pattern disappears. The superposition is gone.
The act of measuring destroys it.
It forces a choice, yes. Which raises the big question, what is measurement? What causes this collapse?
Right, so the particle's in this fuzzy state of possibility. Then we look, we measure. What actually happens? What triggers this collapse?
Okay, so every measurable property, spin, position, momentum, we call these observables, has a matching mathematical operator. The possible results you can get when you measure are specific values called eigenvalues. Now, if the system is already in a state corresponding to one of those definite values, an eigenstate, then the measurement is 100% certain. You get that value and the state doesn't change.
Okay, makes sense.
If it's in a superposition, a mix of states, the measurement randomly picks one of those eigenvalues. The probability of picking each one is given by that Born rule, the squared amplitude. And here's the key. Immediately after the measurement, the wave function changes. It collapses into the specific eigenstate that corresponds to the value you just measured.
So it's like smooth, predictable evolution governed by an equation, the Schrodinger equation most of the time. But then, bam, measurement happens, and there's this sudden random jump, collapse.
That's it, exactly. You've put your finger right on the measurement problem. It's this deep tension. Are there two different sets of rules? What defines a measurement? Where's the dividing line between the quantum system and our, classical lab equipment? It's still debated.
Okay, wow. So at that foundation, finally, entanglement. Einstein's spooky action at a distance. What makes it so different from just normal correlations? Like if I have two glows in boxes and find a left one, I instantly know the other is right. That's not spooky.
Exactly. That's a great analogy for classical correlation. The properties were decided beforehand. Berlman's socks is another famous one. One's pink, the other's green, determined from the start. Entanglement is, well, weirder. Deeply weirder. With entangled particles, their individual states aren't just unknown, they're genuinely indeterminate before measurement. They don't have a definite spin, for example, until one is measured, but the moment one is measured, the state of the other, however far away, instantly becomes definite too. Perfectly correlated or anti-correlated.
Instantly, across space.
Instantly. And this isn't just theory. Bell's theorem and the experiments testing it have basically slammed the door on explanations involving local hidden variables. Any classical idea that the properties were secretly predetermined. It means entanglement is fundamentally non-local and non-classical. You can't mathematically separate the description into independent particles.
Okay, that is spooky. So how do we write these states down? What are the key examples?
The simplest, most fundamental examples are the Bell states. They describe two maximally entangled qubits, qubits being the quantum version of bit 0 or 1. There are 4 Bell states, and they form a sort of complete toolkit for describing two entangled qubits.
Okay.
For instance, one is called OS, 5 plus, it looks like, 1 over the square root of 2 times the combination of 0 OS plus 11, say?
0 plus 11s. So that means if the first particle is measured as 0, the second must be 0. And if the first is 1, the second must be 1.
Exactly. That's a correlated outcome. The two A-psi states show this correlation. 0 eras and 11 are the only possibilities. Then you have the A-psi states, like A, psi minus, which is 1 year CI1.
0, 1 minus 10. So the first is 0, the second must be 1. And if the first is 1, the second must be 0.
Precisely. That's anti-correlation.
So that's where my intuitive inversion idea fits in.
Yeah.
It perfectly describes these anti-correlated psi states.
It really does map beautifully onto them. And notice something else. This leads straight into your elimination of possibilities idea, even before measurement.
How so?
Well, look at that A state again. Young
Yeah.
error in 0, 1 error is 10. What's the chance of measuring 0, 0?
Well,
Or 11 error?
0. They're not even in the formula.
Exactly. The very act of creating this specific entangled state has already eliminated the possibility of getting the same outcome for both particles. Stage 1 of elimination.
Okay, but this isn't just math, right? Particles don't just decide to become entangled. How does it actually happen physically?
It happens through physical interactions, usually linked to conservation laws. A really common source is particle decay. Imagine a particle with 0 total spin decaying into 2 particles, like an electron and a positron, which each have spin. Angular momentum has to be conserved. Overall spin was 0, so it has to stay 0. That means if the electron ends up spin up, the positron must be spin down instantly and vice versa.
So the conservation law forces them into that specific anti-correlated state.
It forces them into the A state, the spin singlet state, yes. Their individual spins aren't set, but they're perfectly anti-correlatedly linked from the moment they're created.
Okay, now we're really getting to the core. Your questions about inversion and elimination. Let's picture it. Alice has one particle, Bob has the other. They're miles apart. They share this A state. Alice decides to measure her particle's spin. What happens?
Okay, Alice measures. Let's say she measures the spin along the z-axis. The instant she gets a result, the entire combined wave function collapses. Remember, Alice is on her OS. It's on her OS. It's a superposition of Alice up, Bob down, and Alice down, Bob up.
Right. So Alice measures, let's say she gets spin up, 0s for her particle A.
If Alice measures 0 OS, the wave function instantaneously collapses. The math involves something called projection operators, but the result is simple. The entire system becomes just 0 O and 1 ALCE. The other part of the superposition, the 1 ALCE possibility, just vanishes.
Poof. So Alice sees spin up, and Bob's particle, way over there, is now definitely spin down. 1 OIP. That's the inversion effect right there, manifested by the collapse.
That's it. And if she'd measured spin down, 1 OREP,
then the system would collapse to 1 OEP, and Bob's particle would instantly be spin up 0A.
perfect anti-correlation realized through collapse. Bob's particle now has a definite state it didn't have a moment before.
Which leads directly to the elimination of possibilities idea. Let's quantify that. How does Alice's measurement change things for Bob?
Before Alice does anything, Bob's particle is in that 50-50 superposition. If he measures, he could get spin up or spin down. Both are potential realities for him.
Okay.
But after Alice measures spin up, let's say, and maybe texts Bob the result, the situation for Bob has changed fundamentally. His particle state is now spin down. If Bob measures his particle spin along the same axis, he will get spin down. 100% certainty. The possibility of him measuring spin up is gone.
It's been eliminated. One of his two possibilities just vanished because of Alice's measurement far away.
Yes. So we see that two-stage elimination you were sensing. Stage 1, entanglement forms. Certain combined outcomes, like 0s or 11 Noger, become impossible from the start. Stage 2, measurement happens. Alice measures, say, 0 Dover. This eliminates the remaining possibility of the 1 Elere, leaving only 0 say or Elere. For Bob, this means his 0B possibility is gone, leaving only one Ellery.
That clarifies it perfectly. Eliminating half the possibilities is a really good intuitive description of what measurement does to the entangled partner. And this isn't just for the anti-correlated states, right? The correlated ones too.
Absolutely. The core phenomenon is always perfect correlation, sometimes direct, sometimes inverse, revealed by the collapse. And the fact it's instant, non-local, and confirmed by Bell tests is why it's so spooky.
Okay, let's circle back to the terminology. We've seen how inversion feels right for the anti-correlation. But you mentioned physics terms are precise. How would a physicist view that word inversion here?
Yeah, it's a great intuitive hook, but inversion isn't really the standard technical term for the measurement outcome itself. For one thing, like you said, it's not general entanglement also gives direct correlations. There is a 11-0 in the phi states. The key is perfect correlation, full stop.
Okay.
And second, inversion in physics usually means something specific, like a symmetry operation, often a unitary one, like flipping spatial coordinates R to R. Measurement, though, this collapse process, it's fundamentally different. It's a non-unitary projection. The state vector gets squashed down onto one specific possibility. It's probabilistic.
So better to say anti-correlation, which is achieved via wave function collapse or state vector reduction.
Precisely. That's the more accurate description of the physics. Anti-correlation via collapse.
Now, you also brought up something really deep. Can this collapse be undone? The inverse of wave reduction, as you put it.
Mm-hmm.
Is that possible?
That's a fantastic question. And in a way, yes, the universe is constantly kind of reversing the effects of collapse through normal evolution.
How does that work?
Well, think about it. A measurement collapses a particle into a definite state, say a very precise position. But quantum mechanics, via the uncertainty principle, tells us that a precise position means a very uncertain momentum.
Right, Heisenberg.
Exactly. So that highly localized wave packet immediately starts to spread out again. It evolves according to the Schrödinger equation, which is deterministic and unitary. As it spreads, it naturally re-enters superpositions, maybe a superposition of different positions, or momenta.
So collapse is like hitting pause and reset to one value, but then you immediately hit play again, and the quantum fuzziness starts spreading out.
That's a pretty good way to think about it. Collapse is a momentary event, a projection onto a definite state. But then, unitary evolution takes over immediately, leading back towards new superpositions. It's a cycle.
Which brings us right back to that core tension we talked about earlier.
Mm-hmm.
Smooth evolution versus this abrupt, maybe even violent collapse. The measurement problem.
Mm-hmm.
And this has led to different ways physicists try to make sense of it all, different interpretations.
Absolutely. Because the math works beautifully, but what it means for reality is open to interpretation. There are many, but two big ones dominate the discussion. First, there's the Copenhagen interpretation. This is the traditional view, the one most often taught initially. Copenhagen basically says, yes, collapse is a real physical process. It's non-unitary, it's probabilistic. It happens when a quantum system interacts with a classical measuring device.
So it accepts the two different rules, essentially.
It postulates them, yes. There's a quantum realm, a classical realm, and collapse is the bridge. For Copenhagen, your elimination of possibilities is real and objective. Those other possibilities literally cease to exist for that system.
Okay. And the alternative, the radical one.
That's the many worlds interpretation, or MWI, proposed by Hugh Everett III back in the 50s. MWI takes a dramatically different path. It says, collapse never actually happens. There's only one rule: smooth, deterministic evolution of the wave function according to Schrödinger. Always.
But then how do we get definite measurement results if everything stays in superposition?
Everett's insight was that the observer and their measuring device also become part of the quantum system during measurement. They get entangled with the particle. So if the particle is in a superposition of spin up and spin down, when you measure it, the entire universe splits.
Splits, like parallel universes.
Essentially, yes. In one branch of the universe, you measured spin up, the particle is spin up, and you are now observer who saw up. In another parallel branch, you measured spin down, the particle is spin down, and you are observer who saw down.
Whoa. So in MWI, all possibilities are realized, just in different worlds.
Precisely. The elimination of possibilities is purely subjective, from the viewpoint of an observer stuck in one branch. Across the multiverse, everything that could happen does happen.
So Copenhagen, collapse is real, probabilities are fundamental, possibilities are eliminated. many worlds. No collapse, deterministic evolution, all possibilities happen in different branches. Very different pictures of reality.
Very different. And there are other interpretations too, but these two really highlight the core dilemma posed by measurement.
So wrapping this up, we've taken these really intuitive starting points, your inversion and elimination of possibilities, and seen they point right at the heart of quantum mechanics. They connect directly to anti-correlation and entangled states, and the whole mysterious process of state vector reduction or collapse.
It really does. It shows a universe that's just fundamentally stranger, more interconnected, and maybe more fluid than our everyday intuition prepares us for. Where measurement isn't just passive observation, it seems to actively shape reality.
And here's maybe a final thought to leave you with. If the universe is in this constant cycle, collapsing to definite states, then evolving back into superpositions, then collapsing again, what does that really say about certainty itself? Is uncertainty just a temporary state between measurements, or is it somehow more fundamental?
Yeah, deep thoughts. And if you want to dig even deeper after this, definitely look into Bell's theorem and the experiments that tested it. Elaine Aspect's experiments and others. They are the bedrock proof that this isn't just fancy math. The universe is non-local in this spooky way.
Yeah.
It rules out those classical hidden variable ideas.
Good recommendation. What else?
For a more modern take on how the classical world we see emerges from the quantum fuzziness, check out quantum decoherence. It doesn't necessarily solve the measurement problem entirely, but it explains how interaction with the environment rapidly makes quantum superpositions sort of fade away from view, making things look classical, often without needing to invoke a fundamental collapse postulate. It's key to most modern thinking.
Decoherence, right.
And finally, if you want to see where this weirdness becomes useful, dive into quantum information science. Things like quantum computing, quantum cryptography, quantum teleportation, they aren't just theory anymore. They actively use superposition and entanglement to do things classical computers and communication systems just can't. It's technology built directly on the spooky,